All right, so it's my great pleasure to introduce Stuart Parkin. Stuart Parkin is both director of Max Planck Institute in Halle on microelectronics, and he is also a Humboldt professor. And he has a long and distinguished career, particularly in the area of materials related to data storage. So I believe, so one of Stuart's sort of accomplishments in this area has to do with discovering how spins couple between multilayers in magnetic heterostructures. And this has resulted in, among other things, dramatic increases in density of hard drives and so on and so forth. And today he's going to tell us, I think, primarily about what he thinks is a really exciting next generation memory storage technology, which he calls racetrack memory. So, Stuart.
Well, first of all, Tyrell, thank you very much for giving me this opportunity to join your summer school. And I apologize, I have a bit of a cold, so I might lose my voice from time to time. Of course, materials are critically important. We heard this morning some very nice talks about using modern methods to identify new materials. But it's very tough to develop methods to identify interfaces, and interfaces are really key to my own research. And what I'd like to do is tell you then about how we could use spintronics to store data. And I'm going to give you a little bit of background over the past, the present, and the future of spintronics. And of course, you're welcome to interrupt at any time to ask questions. And in this movie that you may have looked at, this is a fly-through of the laboratories and that I built since I came to Max Planck, basically since 2018. And basically, we built up laboratories where we can develop materials one atomic layer at a time using a wide variety of thin film deposition techniques. We can characterize them using advanced characterization techniques, and then we can make devices in a small clean room where we have state-of-the-art optical and electron beam lithography, and then measure these devices over a wide spectrum of magnetic field temperature and frequency. So this is what I want to tell you a little bit about. And let me see if I can move forward. Let's see. So by way of introduction, of course, it's, as you all know, it's clear that we're living in a very exciting time. In the last 100 years, we've evolved through different technologies for computing, and the current age of the integrated circuit has come to an end, most people believe, in the sense it's no longer possible to scale the fundamental building blocks of these integrated circuits, which are transistors on the one hand and memory on the other hand. And these devices have been scaled down by 1 billion times in dimensions in the last 40 years, according to simple scaling rules that were set down 40 years ago. However, these rules started to fail about 15 years ago, when it was no longer possible to increase the frequency of operation of these devices because of the high energy consumption. So we need to do something else to go beyond what has happened over the last 40 years. And there are two major areas of computing, which is super exciting today. One is cognitive computing, and this is the concept that we could indeed build devices for computation that could consume perhaps 1 million times less energy than today's devices, inspired by our own computing system, our own brain. Our own brain uses about 20 watts. And this, it is believed, we would need about 10 megawatts to use conventional silicon-based devices to mimic or to compete with our own brain for certain types of operations. So this means there's a huge opportunity to decrease the energy of computing. And as you all know, the amount of energy consumed by computing resources is increasing, and in just the last 2 or 3 years, because of artificial intelligence, increasing dramatically. So we need to do something else. This is one possibility, and I have some projects, which I'm not going to talk about, in neuromorphic or cognitive computing. On the other hand, there's a great excitement about quantum computing. And this is very interesting because we would then move from the digital world of computing today to essentially an analog world. And this in particular makes error correction incredibly difficult. So this is a very interesting potential new technology, but many roadblocks to its implementation. So what can we do going beyond charge? The essence of today's circuits is essentially the electron's charge. You could use the spin. And my talk is really to tell you a little bit about spintronics. However, we're also very interested in using currents of ions. And currents of ions very interesting. You can remove a little bit of oxygen, let's say, from certain oxides like vanadium oxide, and you can turn it from being an insulator into a metal. And you can basically then convert insulators to metals, metals to insulators by adding or subtracting ions. And this is very, very interesting, and I think potentially has enormous ramifications. Again, I'm not going to talk about that, although we are working in that field. And finally, I wanted to mention that we're also undergoing, most likely, a technological revolution when we go from the two-dimensional devices of today to three-dimensional devices in the future. This is something which is incredibly difficult, but the racetrack technology that Tyrrell mentioned at the beginning is innately three-dimensional. So I want to come back to that in the middle of my talk. So if we want to think of a major technological revolution that had enormous impact, this could be Johannes Gutenberg. So now I'm living in Germany, and Mainz is a city in Germany, in the western part of Germany, where Johannes Gutenberg invented the movable type press 550 years ago. And this actually was a major development. It enabled the printing of books, and this, of course, led to the spread of knowledge and the modern world of today. And this book printing concept lasted 500 years. Moreover, even the materials that Mr. Gutenberg invented, an alloy of lead, tin, and antimony to make the movable type, that was used for more than 500 years. So this was a major, impressive technological breakthrough. And this led then to the analog world of information. So this changed after 500 years. About 70 years ago, when IBM developed in San Jose, California, when it was basically pristine, just orchards and wineries, they built a factory to make magnetic disk drives. Eventually, this factory had 20,000 people or so, and was led the disk drive business for many years, till IBM eventually sold the business because it became a commodity. What is a disk drive? Essentially, these are glass disks today. This is a modern disk drive shown here, 3.5 inches in diameter. And on the surface of the disk, you can see here some brown material. Today, that would be a thin layer of a magnetic material magnetized perpendicular to the disk. And the concept is you write regions that are magnetized up or down and read that information back. And as you can see, it's a mechanical device where the disk is rotated at about 10,000 revolutions per minute, and the writing device is moved across the surface of the disk. So it's a mechanical device, which means it's fundamentally a little bit unreliable. Nevertheless, over the last 70 years, the size of the magnetic regions used to store the information, whether they're magnetized up or down, has decreased by more than 1 billion times, so that the information capacity of one of these disk drives today is of the order of terabytes for a single disk. And you can see on the left-hand side how basically one needs to shrink for the size of these magnetic regions. So the point is that if you look today in the cloud, of course, there's enormous numbers of computing systems, but largely speaking, it's all about the digital data. The value is in the digital data and how much of it you can store and access. And so this means our ability to store essentially all digital data today in disk drives. About 70% all digital data is stored in disk drives till today, is the underpinning of all the most valuable corporations in today. So this has had a major impact. Now, the reason why we use disk drives is actually because of a spintronic device. And I want to come back to that in just a second, just to remind you then, I like this article in Science more than 10 years ago, where this change from the Gutenberg world of analog information to the modern world of digital information happened about 15 years ago. You can see the orange devices here are essentially analog devices, and the blue devices are essentially digital devices. And so it happened relatively recently that we could move from the analog to the digital world because the capacity of magnetic disk drives increased so much so that one could store essentially all digital, all data, all knowledge in these disk drives. So what is spintronics? Electrons have a charge, they also have a spin. As you know, it's quantum mechanical, the spin points up or down. And spintronics is really about creating currents of electrons whose spin is oriented in one direction or the other direction, and creating materials in which we can control the passage of these spin polarized currents. This, in essence, is spintronics, and this enables us to build both computing and memory storage devices. So let me go back to the very beginning of spintronics, and this is the concept of this. The simplest concept is something called a spin valve. It's something I invented. Here is copper. Copper is a non-magnetic metal, and if you introduce current from a battery on the left-hand side, the current will be carried equally by spin up and spin down electrons. This is what happens. However, if you have a magnetic material, then it turns out the magnetization breaks time reversal symmetry, and moreover means that electrons with spin up and spin down are scattered at different rates from these magnetic moments. And this leads to, in some magnetic materials, the fact that the current is innately spin polarized. So within a few mean free paths of the introduction of a spin unpolarized current from a battery, the current becomes spin polarized. And in some soft magnetic alloys like nickel iron and nickel cobalt, the current is about 70% spin polarized. This in principle leads to higher resistance in these magnetic layers. However, if you take now a sandwich, which consists here of two magnetic layers and a copper layer in between, then you can see now that if we introduce current from the left-hand side into this sandwich, when the two magnetic layers have their moments in opposite directions, this means that electrons, let's say the red electrons, will be scattered in the blue layer and vice versa. So everywhere the electrons will suffer scattering if the copper layer is sufficiently thin compared to the mean free path of the electrons. The electrons, as you know, are moving in all directions. Now the idea is that if we then switch the magnetic moment of these two ultra-thin magnetic layers, so they're parallel, now the blue electrons will be less scattered everywhere, and essentially the conductivity of this sandwich will be increased. So the idea is we can change the resistance of this sandwich if the layers are thin enough by simply changing the orientation of these magnetic layers. This is what we call a spin valve. And it turns out that if you, and again, I'm not going to discuss all the details, but if you create structures in which you control the orientation of these magnetic layers, then you can, in the presence of tiny magnetic fields, change the resistance of this device as the magnetic moment of one of these layers is redirected by the external magnetic field. And even today, this is one of the most sensitive detectors of small magnetic fields at room temperature. It's based essentially on these nickel-based layers, but the interfaces actually are where the scattering takes place. So by interfacial engineering, we can create these spin valve structures which are sensitive to tiny magnetic fields by using soft magnetic layers, but in which the interfaces where the scattering takes place gives rise to strong spin-dependent scattering and then leads to a large change in the resistance of this structure when the magnetic moment directions are evolved. So this structure was introduced by IBM when I was in research at IBM in 1997 into a magnetic disk drive. And it happened. So the basic concepts I invented in the early 1990s, 1989, 1990, 1991. It only took a few years before this structure made its way into a magnetic disk drive and was used to read the information by reading the fringing fields from the boundaries between successive magnetic bits magnetized in opposite directions, and the field center of the order of 10 Ersteds or so. The actual reading head during the process of reading is only 1 nanometer above the surface of this disk where it is floating on an air barrier. This immediately led to rapid increases in the capacity of a magnetic disk drive because this spin valve could detect regions, magnetic regions, that were approximately 1,000 times smaller than was previously possible. So it led to a 1,000-fold increase in the storage capacity of these magnetic disk drives in a relatively short period of time. And so this is why essentially we can store all digital data today using magnetic disk drives, but essentially it's this spin valve device that makes it possible. So this is the first basically real implementation of spintronics with huge impact. Now, the second implementation was something, again, I'm not going to say much about, but this is essentially a spin valve where the copper layer is replaced by an insulating layer, shown here by this gray region. And now it turns out, just as in a spin valve, metallic spin valve, this device, which is based on quantum mechanical tunneling of electrons from one magnetic electrode to the other one through this insulating layer, leads to even larger changes in the conductance of this sandwich structure. The physics, though, is entirely different. It's no longer spin-dependent scattering. It's now spin-dependent conductance or tunneling through the gray barrier. And the breakthrough here was actually some materials that I published in 2004, in which we showed that you could build a structure in which the tunnel barrier itself acts, even though it's non-magnetic, acts like a spin filter. And the reason is that if you combine magnetic materials in which the spin up and spin down electronic states, spin polarized states at the Fermi energy have distinct character, let's say one set of electrons is S-wave-like, and therefore the wave functions are extended, and the opposite polarized electrons are more D-like and are more localized, and therefore the wave functions are less extended. This means across that gray insulating region, the S-like wave functions can more rapidly, more easily tunnel than the D-like wave functions. And this automatically leads to a spin filtering effect, meaning that the current in such a device can be up to 96% spin polarized electrons with one spin orientation if the insulating layer is sufficiently thick. And this is something I published in 2004 and is now the basis of both sensing devices, spin valve sensing devices using spin-dependent tunneling. And that's been used in magnetic disk drives since 2007. But essentially, all the other concepts of engineering to make it function and be responsive to small magnetic fields are unchanged. I'm going to come back to some of those ideas later. But nevertheless, this tunnel junction enabled even further increases in the capacity of the magnetic disk drive. This is just to show you then this spin valve device where the essential physics is that of giant magnetoresistance. Then the magnitude of the resistance change is at room temperature is just a few percent, 10%, whereas the tunneling magnetoresistance has changes in resistance in one of these junctions when the magnetization of two electrodes is switched from parallel to antiparallel of several 100%, even at room temperature. So this makes them extremely interesting, not only for sensing, magnetoresistive sensors, but also as a memory device. And this is something that we proposed first in 1995, so it's a long time ago. And this is the concept. On the bottom, you can see a so-called cross-point array. You have arrays of wires in opposite directions, and at each intersection, you place a tunnel junction where the current flows perpendicularly through the device from the lower to the upper electrode. And then we could store information, no longer as a sensing device, but as a memory device. We store information as the direction of the magnetization of the moment of one of these layers in the tunnel junction is shown on the right-hand side. And because the difference in the resistance of the device when let's say the rightmost electrode is pointing to the right or to the left, the change in resistance at room temperature can be several 100%. So it's very easy to detect the state of this memory device using a small current. So it's very energy efficient. At the same time, it turns out, and this is what I want to discuss next, you can write this device by simply passing a large current, spin polarized current through the device. This current, because it consists of electrons all polarized in the same direction, carries spin angular momentum that can be used to apply torques to the magnetization and can switch the magnetization from one direction to the other of the electrode that acts like the memory. And by design, we engineer the other magnetic electrode to be fixed in direction. This is the nature of MRAM. So as I said, we proposed it in 1995, but it took a long time from the concept to the application. So in 1999, we actually could demonstrate the first array, a 1,000-bit array of magnetic tunnel junctions. But nevertheless, later on with my colleague Bill Gallagher in Yorktown Heights, we demonstrated a fully functional 16 megabit chip. That was 2005. Nevertheless, it still took until 2019 till MRAM became widely available by all the major semiconductor manufacturing companies, in particular Samsung and TSMC, and it's becoming it's becoming more and more important. It replaces so-called embedded DRAM, which is a charge-based memory, which is volatile, that does not scale. So MRAM can scale to smaller dimensions. It's also non-volatile. It remembers its state in the absence of current. And so it's replacing all sorts of devices today. In particular, electric cars need all sorts of memory, which is non-volatile. And so this MRAM will becoming the main memory used in, let's say, electric cars in the next 2 or 3 years. For example, as one application, it's already used in other devices. So this is a huge success, but it took from 1995 till 2019. So just last December, the head of Samsung Electronics wanted to meet me, and he told me that MRAM now, they've sold several $1 billion worth of MRAM and are expanding their production. The reason why I mentioned Samsung is that when I was at IBM, they supported our research in MRAM. And now that I'm in Germany, they're supporting my research on racetrack memory that I'd like to discuss briefly next. Also wanted to point out that so far, this memory, the disk drive, and this MRAM, like all semiconductor memories, is innately two-dimensional. So if you look at this cross-sectional picture of an MRAM device, mostly it consists of a series of transistors in the silicon crystal surface, which are used and wired to connect to, let's say, the MRAM devices themselves. But it's essentially innately two-dimensional, where the wiring takes place in the third dimension. I want to then briefly mention, what about truly innately three-dimensional devices? Let me just, also point out then that I wanted to mention how long it takes to develop the materials and devices from concept to real disposition, let's say, for MRAM in foundries. It took 25 years. The spin valve sensing device took only 6 years, and that's partly because each disk drive uses a single spin valve device, whereas in MRAM, you have to build billions of devices, all of which have to operate at the same time. So this is intrinsically the difference between the possibility of one of these different technologies and why it took so long in one case versus the other. So I want to switch now to the third. So we had 2 spintronic technologies that are now successful and having major impact. The third one, I think, is even more interesting in my mind. And this is what I call racetrack memory. And it's based on this concept. It's already mentioned, if you take a magnetic material and pass a current through it, the current becomes spin polarized. Therefore, it carries spin angular momentum. And in the bottom left, you can see a simulation or a cartoon of what happens in a magnetic wire in which you have 2 magnetic regions pointing in opposite directions, and there's a magnetic domain wall in between. When you now pass a current of spin polarized electrons magnetized but oriented in one direction, that current can deliver angular momentum to the moments in the domain wall, apply torques, and cause the domain wall to move. And interestingly, all the domain walls will move in the same direction in a single magnetic wire. This is then the essence of what I proposed as a racetrack memory in 2004. And this is a paper in 2008. We published a paper which is very highly cited, in which I describe this concept of racetrack. And here's the concept shown on the right-hand side. You can see a vertical magnetic nanowire, which is a uniform magnetic wire in which it's magnetized in the opposite directions, blue and red. And the information is encoded in the domain walls between these oppositely magnetized regions. So the presence or the absence of a domain wall would correspond to a 0 or a 1. And then the concept is you pass current into this racetrack, and the idea that all the domain walls would or should move in the same direction. Therefore, as you can see in the surface of a silicon wafer, where we would use conventional CMOS circuits to generate the current needed current pulses needed to move the domain walls and to detect them, you could store, let's say, in 1 nanowire, 100 domain walls in the third dimension, therefore increasing the storage capacity over a conventional charge-based memory device with a single memory element per device by 100 times by the numbers of domain walls in this racetrack. And then the idea is in the racetrack, you have a single reading device and a single writing device built into the racetrack to enable you to read the information after you move it to the reading and writing devices. So this is very different from any other memory device in the sense that the information, the data, is physically moved, but without moving any atoms, only by rotating the magnetic moments. And this is crucially important. Typically, memory devices involving the motion of atoms, such as ferroelectric memories, phase change memories, typically have failure mechanisms that prevent their widespread use. So racetrack then would require the billions of these racetracks, each one storing 100 domain walls or more. And so I proposed this in 2002, actually. IBM at that time wouldn't let me talk about it till patents were issued in 2004. And it took us several more years before we demonstrated the basic principle did actually work, that we could move a series of domain walls along a racetrack. And so over the past 20 years, we've undergone a series of, if you like, families of racetracks that we've invented that use different physics for moving these domain walls. And I want to briefly discuss some of these. So the one which I discussed now is called spin transfer torque, wherein a single magnetic material, the current simply by passing through that magnetic material becomes, through spin-dependent scattering, spin polarized. And when it crosses a domain wall, it can adiabatically transfer its spin angular momentum into the magnetization of the domain wall, causing the domain wall to move if you have enough current, enough spin angular momentum passed across the domain wall. And that's what we showed in a paper in 2008. We could move domain walls like this at speeds of about 100 meters per second. So later on, we and others invented or discovered a new torque that is derived from something called the spin Hall effect. So in this case, we, as you can see in this top cartoon, we have a racetrack, but the racetrack, the magnetic layers are placed on a metal layer, which typically consists of its high Z element, strong spin-orbit coupling. And then the idea is that in that metal layer, like platinum, when you pass a charge current into that metal layer, it creates, through the spin Hall effect, a transverse spin current. This is common to nearly all metals and semiconductors. It was discovered relatively recently in metals. Then the idea is the spin current, which is created, turns out it's a chiral phenomenon. This polarization of the spin current is perpendicular in a chiral fashion to the direction of the electric current. The spin current created can then diffuse into the magnetic material, and the spin polarized current then generates torques. And this is called a spin orbit torque because it's generated through spin orbit effects in the metal layers. And so over the last few years, there's been a great deal of interest in exploring different metals that can create, through the spin Hall effect, larger spin currents. And today, the efficiency with which you can convert charge current to spin current is about 3 to 1. In other words, for every electron, charged electron, you can create 3 spin polarized electrons. And so this is very useful, and it's more efficient than the spin transfer torque, in which, as I mentioned, the polarization of the current is only about 70%. So now you can move the domain walls much more efficiently because of the greater spin orbit torques, the greater degree of spin angular momentum that can be transferred through the spin Hall effect in these layers into the magnetic system. So this is today, one would move the domain walls using this spin orbit torques plus another torque, the giant exchange torque that I will try to discuss. And then we could read, how do we read the domain walls? And there are different techniques. There are many optical techniques. But electrically, there are two obvious techniques. One is the anomalous Hall effect. So spin Hall effect is a spin polarized current created in a non-magnetic metal. In a magnetic metal, then you see this an anomalous Hall effect, where typically the magnitude of this transverse voltage is proportional to the magnetization. That's in conventional ferromagnets. Today, one can see anomalous Hall signals even in systems without any magnetization in chiral antiferromagnets, for example. And I'm going to briefly come back to that later if there's time. Finally, we could integrate a tunnel junction directly into the racetrack. So on top of the racetrack, which is a magnetic film in which the magnetization is perpendicular to the layer, we can create an insulating layer and then a counter electrode to form a tunnel junction. And as you can see in this cartoon on the top right, when the domain wall will move, then the magnetization under the tunnel junction changes from up to down, and the resistance through the tunnel junction will change. So if you like, this then is a sort of summary of the evolution of the racetrack technology over the last 20 years. We've evolved from, in racetrack version 1.0, simple, soft magnetic materials in which we use this spin transfer torque to move the domain walls, to the spin orbit torque to the spin transfer torque, the same thing, but in materials in which we've generated large magnetic anisotropies perpendicular to the racetrack so that we can shrink the size of the domain walls considerably, 100 times beyond the soft magnetic materials. And then finally, in racetrack version 3.0, we use spin orbit torques to manipulate the domain walls via the generation of spin currents through the spin Hall effect. And then finally, the most important development is this thing, version 4.0. And this is a synthetic anti-ferromagnetic racetrack. And the reason for this is that the domains and the domain walls, as I mentioned earlier, create stray fields. And this means the strong interaction between the domain walls or domains in one racetrack and the neighboring racetracks, or even in the same racetrack. And on the nanoscale, these stray fields increase inversely with the size of these devices, reaching hundreds of wosteds. And this means that it's impossible to build a racetrack without eliminating the stray fields. In fact, it's impossible to build spin valves without eliminating the stray fields from the two magnetic layers in the spin valve sandwich or in the magnetic tunnel junction. Similarly, you have to eliminate the stray fields. In all cases, the solution is a synthetic antiferromagnet, which is something I invented in 1991 and was used in the very first spin valve devices. The synthetic antiferromagnet is very simple, as shown in this cartoon in racetrack 4.0. In this case, we build on top of the racetrack a second identical racetrack coupled through a thin layer that the thin layer, metallic layer, gives rise to something called the Rudiment-Kittel interaction. And I showed this in the 1989, 1990, that one could see this effect through nearly all the noble and transition metals in the whole periodic table. What does it mean? It means that in the presence of a magnetic layer next to one of these metallic layers, the metallic layer becomes magnetic, but it will become magnetic to form a spin density wave. And this leads to an interaction between two neighboring magnetic layers that are separated by this spacer layer, which can be antiferromagnetic or ferromagnetic. And it turns out if you use an ultra-thin layer of ruthenium or osmium, then the two magnetic layers are extremely strongly coupled antiferromagnetically. And therefore, we can create a racetrack in which the top layer of the racetrack has a magnetization exactly opposite and equal to the lower racetrack. This means we essentially eliminate the magnetization. And it turns out when we did this, we discovered that the spin orbit torque generated again in this spin orbit coupling layer we also give rise to a giant exchange torque related to the strength of the antiferromagnetic coupling the upper and lower racetrack. And so it turns out in this system, the domain walls will move at speeds exceeding 1 kilometer per second, 5 to 10 times faster than in an identical racetrack in which the upper and lower electrodes upper and lower layers are coupled ferromagnetically. So this synthetic antiferromagnet turns out not only to eliminate stray fields, but it gives rise to a highly efficient current-induced motion of the domain walls. This is essentially why racetrack is possible today. So this is essentially what I've discussed. We've create a racetrack. Shown on the right-hand side, you can see schematic representation on the top of a simple ferromagnetic racetrack. The green and blue layers can correspond to ultra-thin layers of cobalt and nickel, each layer a few angstroms thick. The orange layer would be this platinum layer, which we generate the spin-orbit torques. And on the bottom, you can see a synthetic anti-ferromagnetic racetrack, which again consists of these atomically engineered cobalt-nickel cobalt layers. The interfaces break symmetry and give rise to strong perpendicular magnetic anisotropy. The yellow layer is this ultra-thin layer of ruthenium that leads to this strong anti-ferromagnetic coupling. And then you have a synthetic antiferromagnet in which the domain walls under the current pulses can be moved at very high speeds exceeding 1 kilometer per second. And on the left-hand side, you can see optical images of racetracks, which are microns wide in order to detect the domain walls. But we take an image using something called the magneto-optic Kerr effect, in which the polarized light is reflected from the surface. The planar polarization is rotated to the left or right, depending upon the direction of the magnetization in the racetrack. And then we can detect the motion of these domain walls by applying a current pulse, measuring an image of the domain walls, applying another current pulse, and seeing how they've moved. So we can detect their velocity. However, these optical techniques, well, they have enabled us to develop all this interesting physics. Nevertheless, do not enable us to detect domain walls in ultra-narrow racetracks, which are important for technology. So I just wanted to make the point that to explore the materials for these racetracks is non-trivial. They consist of a sequence of ultra-thin layers, a few angstroms thick, maybe 10 or 12 layers, all of which have to be engineered to create all the properties needed to make racetrack possible. Nevertheless, and this is one of the reasons why in Germany I built a system in which we have a series of deposition chambers shown here, one of which I call Mango. This is a homemade device in which we have up to 44 sources, magnetron and ion beam sources, so we can explore a wide range of materials. It's totally automated. And so we also want to use artificial intelligence, machine learning, based on the thousands of structures we make to see whether we can improve the speed at which we can create new materials for racetrack and other applications.
So Stuart, if can I interrupt and ask a question?
Sure.
Actually,
Yeah.
so you showed the optical Kerr imaging of these
Yeah.
racetrack memories.
Yeah.
You know, are there optical techniques people have used with shorter wavelength light or other tricks to try to look at things on the same kind of racetrack memories, but built at sort of nanometer scales? That's
Yeah, so far that's very tough. So you could, for example, imagine using scanning near-field optical microscope. We actually have one, which has an optical resolution of 20 nanometers. However, that technique does not allow, doesn't preserve the polarization of the light. So it's very difficult to detect magnetic structures, maybe not impossible. But to date, optical techniques, as you said, you can reduce the wavelength, but nevertheless, it's still restricted to, let's say, a few hundred nanometers. So I'm going to tell you how we can do this using integrated devices for reading them. That's what I want to briefly discuss next. So it's not possible optically, it seems, maybe SNOM in the future. But so we'll skip this, and I'm going to skip this. This is basically just summarizing the different types of physics involved, which is interfaces to create perpendicular magnetic anisotropy. And it turns out, I come back to this later maybe, it turns out that what is critically important to make this racetrack work is the domain walls themselves are chiral. So it turns out maybe it's really important that they are chiral. And the reason why they're chiral is because of this platinum underlayer. So the same layer in which we generate spin currents through spin Hall effects, the interface between that layer and the magnetic layer leads to a broken symmetry and leads to something called a Diliginsky mirror interaction, which means the moments at the interface want to be perpendicular to one another in a chiral fashion. And it's common to many heavy metals. And so let's say in these domain walls, when we rotate from a up direction, a red to blue, then you can see it will rotate in a clockwise direction, or it could be anti-clockwise, depending upon the material. And this means, let's say, as we rotate from red to blue, you can see that green arrow, that's the direction of the magnetization in the domain wall. It's a nail wall. And the blue to red, the green arrow you see is reversed, because it's clockwise interaction defined by this Delezinski-Marie interaction, which also makes the domain walls have a certain structure. It's called a nail wall, in which the magnetization rotates from up to down in a plane perpendicular to the wall as shown here. And I'm not going to discuss, there's also a very important proximity-induced magnetization in the platinum layer, for example. The spin Hall effect I'll briefly mention, and the synthetic antiferromagnet I already mentioned. We have to design the magnetization everywhere in the racetrack to go to zero to avoid stray fields that cause significant interactions. So then this is, briefly, so instead of using optical techniques, we could use, and as shown here, we could use optical techniques using white light, long wavelengths, effectively to monitor the domain wall motion, even in racetracks that are only 200 nanometers wide. So on the right-hand side, if you look at the bottom, you can see a racetrack which is 1700 nanometers wide. Using Kerr microscopy, this technique of measuring the change in polarization of the light, we detect a single domain wall as we apply single current pulses to move it along the racetrack. We take a picture. You can see the black region and gray, that's the domain wall. We create a current pulse into the racetrack. The domain wall moves to the right. You can see, and then each time we inject a domain current, we take a picture and we can see the domain wall moving. So in each of these set of sequence of images shows a racetrack with dimensions varying from 1700 all the way down to 200 nanometers wide, where we can still detect the motion of a domain wall, but very poorly. And then what we found is, if it's a surprise to us, that the velocity of these domain walls varies very little with the width, so the same current density. And the reason why that could have been a problem is that the edges of the racetrack, if they always have some roughness, because during the lithographic processing, you always create some line edge roughness. And this could lead to pinning of the domain walls. However, we found that although the threshold current to move the domain wall initially increases a little bit, it only increases by about a factor of 2 as we shrink the width of the racetrack. You can see here from 1700 all the way down to 200 nanometers. And on the left-hand side, you can see a typical velocity of the domain wall as a function of increasing current density. Low current densities, the domain walls don't move. There's a threshold current density above which they move, and the velocity increases as we generate more torque from the spin polarized currents. So we were supposed to talk a little bit about materials, and materials are very critically important. Turns out the interfaces are key to everything here. And by manipulating the interfaces, even by the introduction of a few sub-monolayers of certain metals, we can change this threshold current, for example. We can reduce it by a factor of 10. It turns out this was important. Samsung, who supported some of this work, wanted to consider using racetrack to replace VNAND, the densest flash memory today. And they wanted the domain walls to move very slowly. That's a very slow technology. So they wanted us to demonstrate we can move the domain walls at very low current densities. And we demonstrated, indeed, we could reduce that threshold current density by more than a factor of 10 by changing the materials. And in particular, a very interesting material is shown on the right-hand side. Instead of using platinum, we found that there's a certain family of materials, in particular, let's say iridium and aluminum, forms so-called L10 structure, in which even at room temperature, it will form a perfect atomic layering structure with a layer of iridium, a layer of aluminum, a layer of iridium, a layer of aluminum. It's fantastic. And this happens for a large family of these materials. And it turns out we discovered in these materials that by tuning the composition, let's say in this case of iridium and aluminum, we can increase the resistivity by a factor of 10, and this leads to enormous spin-dependent scattering, leading to enormous values of the so-called spin-Hall angle, which is the ratio of the numbers of spin-polarized electrons created for every electron in the current. And this leads to, again, reduced threshold current densities, because the larger the spin-Hall effect, the more efficient is the motion of domain walls and the torques that can be applied. So here I just wanted to point out there's a lot of very interesting materials engineering that we could use to create new materials that can substantially improve the efficiency and other aspects of this racetrack memory. Now let's just briefly then looking again at how can we shrink the size. We need to prove to the companies like Samsung that racetrack will work at relevant length scales, which means essentially sub 100 nanometers. And so to do that, this on the left-hand side, you can see a cartoon to scale of the magnetic racetrack, a simple ferromagnetic racetrack on a platinum layer in which we use to create spin currents. And we build a wing. I don't know if you can see this. The platinum layer is designed to be slightly wider than the magnetic layer. Now we detect the anomalous Hall signal created by current passing through the magnetic material via the platinum Hall bars you can see here, platinum electrodes placed along the racetrack. It turns out, very interestingly, by changing the width of this platinum wing, the Hall signal that is created can be used to detect the domain walls a long way from the electrodes themselves, which are labeled here by this Hall bar. So this is an amazing finding because it means we can actually see a domain wall everywhere along the racetrack by having a series of these electrodes to detect the Hall probe at different places along the racetrack. But by designing the width of these platinum wings, we can detect domain walls that are up to 20 times further from the electrode position as the width of the platinum wings. So we have a paper that's about to be published in Science that discusses this in more detail, and is shown on the right-hand side in this figure, shows that by changing the width of this platinum wing, we can detect domain walls which are up to 20 times further from the electrodes, Hall electrodes, than is the width of the wing. So it's quite amazing. And this has enabled us then to follow the individual domain wall as it moves backwards and forwards along a racetrack as we apply current pulses. These are 5 nanoseconds long in one direction and then the opposite direction. So the individual domain wall can be moved all the way along one racetrack from the left to the right, back and forth. And as we increase the intensity of the current pulse, you can see we need smaller numbers current pulses to move the domain wall from the left to the right. The resolution with which we can detect one domain wall is just a few tenths of nanometers. And we can do this in racetracks that are up down to 73 nanometers wide. So you can see here, this is the motion of a domain wall, single domain wall in a 73 nanometer wide racetrack. In the bottom left, you can see the platinum electrodes and where we detect Hall signal, and the wing where the platinum layer is slightly wider than the racetrack. And you can see here we're detecting the Hall signal at 4 positions where the domain wall is positioned along the racetrack with a sensitivity of a few tens of nanometers, and we can position one domain wall with respect to another one with a spacing of better than 100 nanometers. So all of this means that basically we built racetracks now at technologically relevant length scales and demonstrated that we can detect individual domain walls in these racetracks. And now I just wanted to mention, we're also very interested in a simpler racetrack shown here on the left-hand side, where we integrate a single magnetic tunneling junction on top of a racetrack, and we move the domain wall from the right-hand side to the left-hand side by current pulses, a single current pulse. Here we're using current pulses that are only 500 picoseconds long, and we're detecting the change in state of the tunnel junction. So you can see we can build a racetrack which is super fast a single domain wall. This type of racetrack could replace the fastest memory today, which is static random access memory, would have a smaller form factor, would be non-volatile. This is a very exciting possibility. So this is what we have. We can imagine racetracks that could store vast amount of data, or we can imagine racetracks that can store individual domain walls. And in that sense, racetrack also has this very interesting possibility. You could build long racetracks and decide to store a single domain wall, and then it will be super fast to access that information. Or you could store 100 domain walls. It would take longer to access 1 bit. You'd have to move 100 domain walls. So the same technology can be used for ultra-fast and ultra-dense. So we think this is very interesting. So now I think I'm running out of time, so I'm going to talk briefly about 3D racetrack memory devices. And this is some very nice work by a PhD student of mine, Kei Gu. And what he did, he used a technique, I think it's very elegant, that which has been used over the years, but most recently by Harold Wang at Stanford. Harold used this strontium-3 aluminum-206. It's basically a water-soluble oxide layer. So we ourselves make this by pulsed laser deposition. And on top of this, we make a racetrack using first magnesium oxide and then this platinum cobalt nickel cobalt structure. And then what we do, what Kei does, he dissolves the strontium-3 aluminum-206 layer in water on a 1 centimeter by 1 centimeter substrate. And then he floats off the racetrack on top of the water, and then we can transfer it on something else. And what we do is we pre-prepare a sapphire wafer, in which in the top right, you can see we made these little hillocks, and we make the racetrack on basically to cover this hillock. And this can be seen on the bottom left in E. You can see in this cross-section transmission electron microscope image, you can see the 3D racetrack is the black line. That is essentially, you can see the black line. It's almost following the hillock in the aluminum 2 or in the sapphire substrate. So it seems to work. And then what we found was that the domain walls can be moved through this essentially 3D racetrack. So it's the first attempt to create a truly three-dimensional racetrack. And we found that the domain walls could be moved as efficiently with the same velocities in this racetrack, which has basically been freestanding racetrack that we've gone through this process of dissolving this water-soluble oxide layer and then transferring this 10 nanometer thick racetrack film onto a substrate. So I think this is quite remarkable. And the TM image shows a hillock which is 0.3 microns tall, but we actually made them up to 1 micron tall. Finally, let me show another method for 3D fabrication. And here we've built, another one of my students, Andre Farina, built a technique. It's called a technique. It's not showing it, but in principle, we should show it. We basically have a super resolution optical laser beam with a very high intensity, and that is used to cause polymerization of a complex polymer mixture, which includes some kind of photosensitive component. And in this way, we can build three-dimensional structures. So the reason for doing this, it's a super resolution microscope, and we can build structures from polymers with a pixel size of 50 nanometers, which is several times better than any commercially available 3D printing system. So on the right-hand side, you can see some structures that Andre built just to demonstrate the possibilities. And the idea is you build like a scaffold on which we then place the racetrack by sputtering. And this is what we did here in 2. You can see an image of the polymer scaffold in which we've designed it. So instead of having a flat surface, it has a curved surface. And we were exploring the interaction of three-dimensional geometrical curvature, chirality, and the chirality of the domain walls that I mentioned before. And we can see that the geometrical and spin chiralities can oppose or add in interesting ways to increase or decrease the domain wall velocity. So we have a paper on this under review. not going to say much more about this, but this concept of chirality, I haven't had much time to discuss this, is really interesting, and combining geometrical and spin chirality is super exciting. So in this regard, I think I'm going to run out of time. So I think maybe I skipped this part. I was going to tell you something about skyrmions. And these are complex nanoscopic objects in which chirality plays a key role. And you can see them here. These are basically in a magnetic system, typically which has perpendicular magnetization, has an anisotropy direction. Then it turns out, instead of forming a uniform magnetic structure under some temperature and field regimes, the structure will automatically form an arrangement of small nanoscopic objects, which are typically circular, in which the boundary has a chiral structure stabilized by this chiral Dzyaloshinskii-Mirror interaction, which lowers the energy of the system. And prior to our work, then the systems that had been found were something called a block skyrmion. Outside of this block skyrmion, the magnetization is pointing up. In the middle, it points down. And as you go across a radius, the magnetization rotates in a plane perpendicular to the radius as shown here. And the nail skyrmion is similar to the nail domain wall I mentioned earlier, in which the magnetization rotates from an up direction outside to the opposite direction inside. And it rotates from up to down along the radius, as shown in this cartoon. These are not cartoons, these are actually simulations, micromagnetic simulations we carried out of each of these objects. And in the middle, you can see what's called an antiskyrmion. And it turns out that if you have a low symmetry magnetic material of a certain type, then the Dzyaloshinskii-Mirror exchange interaction changes sign along different directions in the crystal structure. And this leads to a boundary which consists, some parts are nail-like and some parts are block-like. And as you go around the circumference, you rotate from a nail-like to a block-like structure, changing also the chirality. So well, how do you detect these objects? You typically detect them using, in a transmission electron microscope. In this case, we would take a single crystal, we would cut a flake, which is thin enough to be electron transparent. In our case, we have a 300,000 volt electron beam that's passed through this device, and this magnetic material will scatter the electrons to the left or right, depending upon the component of magnetization in the plane of this structure, which is perpendicular to the electron beam. And then we can actually calculate what we would expect to see. And these are so-called Lorentz images of a block skyrmion on the left-hand side. It turns out that the magnetization components in the plane of this block skyrmion cause the electron beam passing perpendicular through it to be scattered towards the middle or to the outside. And a nail skyrmion, because the different components of the magnetization in the plane will cause the beam to be rotated around the circumference. So there's you cannot see anything in the nail skyrmion. And an antiskyrmion, we would expect to see, we calculated this clover leaf-like structure, two white regions of increased electron intensity and two black regions of decreased. And that's actually what we saw on the top left. We saw an antiskyrmion for the first time in a complex Heusler compound, which had the appropriate symmetry that was predicted to display this antiskyrmion. So why are these interesting? These objects, in principle, have some topological protection and could be used as memory bits. Now, until our work, a single crystal, typically, depending upon its symmetry, would display a nail or a block or an antiskyrmion. And then we discovered, I'm going to skip all this, we discovered that in some cases we could see another type of object, an elliptical block-like skyrmion in a system that otherwise would show antiskyrmions. And then we proposed we could use then this for racetrack. We could store information in an antiskyrmion or a skyrmion in the same material. This certainly is possible, but not trivial. Now, I think I probably should. I know I was finally going to talk a little bit about superconducting spintronics, but I think I'm running out of time. So I think I should probably just stop here. And basically, I've spent too much time telling you about spin valve sensors, which are based on spin-dependent scattering, magnetic tunnel junctions, which are based on spin-dependent tunneling. Spin valve sensors are used in the resistive form or in the tunneling form today in magnetic disk drives and enabled, roughly speaking, 10,000-fold increase in the storage capacity of magnetic disk drives, so that 70% of all digital data is stored there. A magnetic tunnel junction we first proposed in 1995 could be a very interesting memory, magnetic non-volatile memory, and it finally became such a foundry technology 5 years ago. And it's already replacing several forms of conventional charge-based memories. And I briefly introduced you racetrack memory. It's been subject of mine for more than 20 years. It's fantastically exciting and interesting. We've evolved the physics from what was possible when we started 2008. We could move domain walls at speeds of 100 meters per second. That was corresponded to 100% transfer of all the spin angular momentum created through this spin transfer torque to the domain walls. But now we can move them more than 10 times faster using spin orbit torques plus exchange torques in synthetic antiferromagnets. And we've recently demonstrated we can scale these racetracks to dimensions below 75 nanometers, which is very close to what is needed technologically. And they promise a memory storage device which is non-volatile, very high performance, 1,000,000 times faster than today's magnetic disk drives, with form factors an order of magnitude smaller than a disk drive, much lower energy, and complete reliability. So it's amazing that there are 3 successful spintronic technologies based on creating and using spin currents in different ways. So I thank you very much for your attention.
Yeah. So thank you. We probably have time for a quick question or two. Does anyone have any questions? Yeah, Oleg.
Thank you. Very nice talk, Stuart. So this is more of a transfer torque mechanism for driving domain walls in the same direction, regardless of whether it's from up to down or from down up. What is there a good understanding of that, or is it still phenomenological mostly?
No, there's a good understanding, and it's only possible when the domain walls have the same chirality. If they have opposite chiralities, then it's not possible. They would move in opposite directions. So we understand, of course, the spin orbit torque. I think maybe what you're referring to, it turns out that the spin Hall effect typically is regarded that the spin currents that generated have a spin polarization which is perpendicular, orthogonal to the current direction. And it turns out today, just recently, this very interesting work where the direction of the polarization of the current could be along the current direction. If that is the case, you could use that longitudinal spin Hall effect to manipulate 2 terminal devices. This could have enormous impact, let's say a magnetic random access memory. Otherwise, I would say so I think you're correct in the sense that the nature of the magnitude of the spin Hall effect, I would say that's less well understood because there are 2 origins, can be intrinsic through Berry phase effects, but there's also extrinsic effects through scattering. And indeed, the system I mentioned is iridium, aluminum, also many other members of that family show enormous spin Hall angles, which are mostly extrinsic. So I think that's where I think there's a great deal of understanding, but not perfect. And secondly, the physics of the interface itself. So once you generate spin currents, let's say in iridium, aluminum, in platinum, the spin current has to diffuse across an interface into the magnetic material. And the transparency of that interface is very poorly understood. And we were the first to show, I don't know, 6 years ago, that transparency plays a critical role. It's, let's say, if you take platinum and a nickel iron alloy, or platinum and cobalt, the transparency is twice as high for cobalt as it is for permalloy. So typically you measure spin Hall angles through these spin orbit torques. And so if you don't include this transparency, you really cannot understand the magnitude of the spin Hall effect itself. So I think this is where there's very little understanding. The interfacial transparency, which plays a critical role. Understanding and improving on that could have major impact.
Thank you. And then, so obvious follow-up question there is, are there materials or structures known where the successive domain walls have opposite chirality?
No, that's not true. They always have the same chirality or random chiralities if you don't have any, let's say, Dzerzhinsky mirror interaction.
Okay. So it's just the DMI biases it to select a single chirality, and if you don't have it, you get random.
That's
whatever.
correct.
Okay. All right. Any other last questions? Sure. Okay.
Thanks a lot. You mentioned a super resolution microscope that you used for nanofabrication. Could you explain a bit how that works? Particularly, how do you go below the resolution limit of the typical light wavelengths?
So this is, as you know, the technique that won a Nobel Prize a few years ago, and it turns out one of those Nobel Prize winners is a Max Planck director and formed a company. So we bought from his company a microscope which is designed to have this super resolution capability. So that basically uses special lenses. So you design the laser beam and combinations of laser beams and lenses that enable you to basically create a intensity of the beam which exceeds a certain value so in other words, if you like, conventionally you cannot achieve resolution beyond the wavelength of the light depending on the lens. However, there's a profile to the intensity of that laser beam, and what super resolution does is uses the intensity above some threshold. Therefore, that enables you to write at dimensions smaller than the wavelength of light. It's basically, this is the idea. It's really due to the intensity profile of the beam. We use it basically, if there's a threshold above which we could cause polymerization, above some threshold, then that will be a threshold that can be smaller than the diameter of the beam. That's what we use.
Yeah, so my confusion came from the fact that so what you're describing is a STAT microscope. Yep. And what basically happens there that fluorophore is deactivated by a second laser beam. But if you do that on a photoresist, then basically you still have several beams present, and I would have just expected that they all end up exposing the photoresist. So I can see how that works for microscopy, but not necessarily for lithography.
No, in our case, you're right in the way that was used for STED microscopy. What we are doing though is something else. We're using doing this three-dimensional printing. So all we have to do is have a threshold for polymerization above some intensity level, and the beam then is designed so that intensity level is achieved only in a small, tiny portion of the beam. That leads to our ability to polymerize at very tiny dimensions. So it's
so it's just playing with intensity that in a very narrow region you're above a threshold effectively.
That's all. Yeah.
So it's a multiphoton excitation that it's relying on, I suppose.
Yes, it is multiphoton. Exactly right.
Okay, thanks.
Okay. So I think in the interest of time, let's thank Stuart again for the wonderful talk.
Thank you.
Thank you, Stuart.
Okay. I say goodbye. Thank you.